Okay, we will continue our survey of recent observational results with a talk by Hector Gil Marin from Barcelona, who will tell us about recent age measurements.
Right, thank you. So yeah, what I'm going to be talking about is essentially about H0. This H0 is a hot topic in cosmology, as you may know. Every week there are several papers solving H0 tension. But so what I just for an introduction for those who doesn't know, H0 is essentially a direct is the tension that arises when we try to measure the expansion history of the universe today from a direct measurement, essentially based on supernovae calibrated with Cepheids, and we compare it with inferred values from CMB anisotropies, for instance, Planck. And you see now that the tension is of about 5 sigma. So if we believe that there are no systematics in the measurements, and we understand our error bars, so it means that essentially we need to modify lambda CDM because it's wrong. And then the question is how to modify it. So a possible approach is just like a piecewise lambda CDM, essentially assume that lambda CDM behaves with like different parameters at early and later times. But then another question is how other observations fit into this picture and where essentially BO from large-scale structure fits in this picture, and whether this BO is essentially relying on late time lambda CDM or early time lambda CDM. So if we want to measure H0, we need essentially calibrators. So we have standard candles, standard rulers. So let me briefly go through the very basic things, how these two different approaches measure H0. So from the direct determination of H0 from supernovae, we essentially take a standard candle as the calibrator for the what is called cosmic distance ladder. So essentially, this cosmic distance ladder plays a role based on two objects of our universe. One is the supernovae, which has supernovae type 1a, which has an intrinsic luminosity. Essentially, there are explosions at fixed mass. And then the other is Cepheids, which are pulsating stars that their pulse is essentially related to the intrinsic luminosity. So the idea is that we calibrate the distance to nearby Cepheids with parallax, and we calibrate these periods to brightness luminosity. Then we look for further away Cepheids that they are hosting. They are hosting the same galaxies that supernovae type 1a. So we can essentially infer the distance and then calibrate the supernovae type 1a, and then we'll go to further away distances where the Cepheids are no longer detectable. But then we can infer distance to the supernovae, which are already far away, that they are already in the Hubble flow. And with the measurement of redshifts of these supernovae, that we know velocity and distance, and essentially this is a direct determination of H0. So the BO feature in the CMB, that was a PDF, okay. Sorry, then you missed the movie. So the BO feature in the CMB essentially is this perturbation that travels through the plasma made by photons and baryons until recombination, when this perturbation doesn't travel anymore. And then on the top of the peaks of this overdensity end up forming galaxies, and at later times we can measure galaxies at those peaks and infer the BO at later times, and this BO feature at different distances serve as a calibrator. So in the CMB, essentially this works in the following way. So if we want to use the BO in the CMB, we do essentially a spectral analysis of the perturbations of the CMB, and we can essentially determine the angular feature of the sun horizon scale at that time. So this angular feature essentially is related to the distance to the CMB through this equation. So, and this feature is measured very, very well. I mean, the precision Planck measuring this feature is like extremely, extremely precise. So also Planck infers by essentially looking at the ratio and the height of the peaks. It can infer other quantities of the lambda CDM model, such as this omega h square. So with these measurements, and assuming that we understand the physics of the early universe, then we can also infer the absolute size of this sun horizon scale. And essentially by taking this ratio, then we infer from CMB this H0 value. Obviously, you see this is like an extrapolation for like super early times to the expansion today. So we need to assume that we know everything in the middle and then we understand things happening here, which is not trivial, but okay. So another thing is the BO, but instead of on the top of the CMB surface in the galaxies, and galaxies also at different redshifts. So this is similar, but not exactly the same. So in the same way as for the CMB, we have some sort of angular BO, which is related to the distance to dust galaxies, and then through the expansion history time between now and then. But unlike the CMB, galaxies have 3D volume, so we also can measure BO along the line of sight. So we have two measurements of BO at the one redshift bin. So essentially taking the ratio, we cancel out this H0 dependence, and we can get like a very good measurement of E of Z. This is essentially called Alko-Paczynski. I have to say that most of the information on this E of Z from actual spectroscopic surveys is not coming from the Alko-Paczynski itself, but also from taking ratios between the BO at different redshift bins. So essentially taking ratio, not this with this, but this with another distances. So this gives like a very, very good determination of E of Z, which is essentially omega matter, under the assumption that lambda CDM is flat. Okay, so we can now go into here and say, well, I can essentially, if I know what E of Z is, I can essentially take out this out of the integral, put it here. I measure the angular BO on the galaxies, and I infer essentially this quantity, H0 times RS. And this is what BO measures. Okay, so if by some means you can infer RS, either by you take it from Planck or you take it from BBN, you take this omega baryon, then you can infer essentially RS, and then you can measure H. But then this is assuming some early time measurement, of course. So another way, like a summary of what I explained, we have like several ways of measuring H0. We have supernovae with the surface as a calibrator, main assumption, non-cosmological things, such as period luminosity relation, physics of the supernovae, and it essentially relies on late-time physics, or late-time astrophysics in that case. So the BO in the CMB, the calibrator is the sun horizon scale at CMB times, and the main assumption is lambda CDM at early times. And this is an early measurement of H0. And for the BO in large scale structure, as I said, there's no calibrator, but there's no measurement. And the only assumption it makes is isotropy and homogeneity. But combination with BBN, this converts into what is called inverse distance ladder. We calibrate our BO measurement at super early times, and we extrapolate it up to now. The assumption is that we understand period combination physics, and this converts into an early time measurement. But we also can calibrate BO with surface, and this is actually a distance ladder. And in that sense, assuming that all this physics is understood, then we can actually not measure H, but measure RS. So this is another way of looking at it. So we have omega matter in here, RD and H0. So with BO only, measurement of E of Z without any calibration with any other assumption, we measure very well omega matter. In terms of H0, we have a perfect degeneration with RD. We are measuring H0 times RD. And now we can combine with things, right? So if we combine with BBN, essentially BBN determines RD. This determination is in very good agreement with CMB, in this case Planck, and we get a low value of H0. We can do also the other way around. We can calibrate with distance ladder, and then we are calibrating essentially at a high value of H0, and what we get is a low value of RD. And even if we allow for like non-standard lambda CDM, you see that once we put CMB on it, there's no enough space that this moves away from low values. So we have another point here, which is the BO plus BBN, which essentially is relying on early time assumptions, and it's low. Okay, so how can they extend this picture and check for potential systematics or new physics affecting these different calibrators of these different assumptions? Are there other late time calibrators? Are there other early times calibrators we can rely on just to make sure that there are no systematics here or here? So, okay. So if we want to solve this tension, I mean, we have to be aware that we have already measurements there, right? So we have essentially this angular BO odd CMB time measured with extremely well precision, right? So if you want to essentially modify the early time physics, so you want to essentially believe that lambda CM is wrong, H0 in reality is high, but we are assuming a wrong assumptions on our early measurements. So what we have to change in order to increase the value of H0 from 68 to 73, 74, there are essentially two ways keeping this angular BO on the CMB constant. One way is to increase the value of H0 by reducing RS, right? So we have this degeneracy. So for instance, an increase of H0 by 7% that would solve the tension. It means that we need to decrease RS by 7%, essentially by decreasing the expansion history at early times before recombination. In this case, the late time E of Z is unchanged, but we have to do this not messing up with CMB CLs. On the other way, we can say, well, I believe on early time physics, this is correct. The problem is at late times. Okay, so you need to increase H0 by 7%, but now you have to change the expansion history at later times to compensate somehow between 0 and the combination times, but in practice, this happens at essentially before redshift 10. In that case, RS would remain unchanged, but you have to be careful to not mess up with the BO of large-scale structure measurements that they are essentially giving you E of Z at later times. It's not so trivial to like essentially modify this without touching this. So other late times calibrators, such as other ways of calibrating distances not based on supernovae. I'm not going into detail on this, but essentially all seems to be pointing towards high values of H. So this is some sort of indicator that it might be something wrong with here. So, okay, so let me just change a bit of topic before coming back to this. And this is if we think of large-scale structure, which information can be extracted essentially from the power spectrum or from the bispectrum. So the standard analysis so far we've been doing is actually to exploit this Arco-Paczynski effect, which is based on background physics from the galaxies. And this is essentially our measurement of the angular diameter distance and the BO along the line of sight in terms of the sun horizon scale as I've seen. And there's another observable that is the redshift space distortion, which is essentially measuring the anisotropy effect due to peculiar velocities. Fine. Is there any more relevant information apart from essentially BO and RSD? So the answer is yes. So we did this project with my former student, Samuel, which is now in Edinburgh. And what we wanted to test is, okay, we have our galaxy catalogs. You measure the summary statistics out of it, and then you do a BO and RSD analysis. You compress this data in these observables, and then you, under some lambda CDM assumption, you measure a series of parameters. Fine. You can actually do this by skipping this step and directly fitting your nonlinear power spectrum model to the power spectrum statistics and then get those as well. And then the question is, are those the same? So the answer is no, they are not the same. They are quite different. So this is a plot from that paper that exemplifies these differences. So in blue is this full modeling of the direct fit of the lambda CDM parameters to the power spectrum data. And you see the constraints in this particular plane, which are in blue. And then you have like constraints from RSD and BO with reconstruction and everything, and you get the orange constraints. So there is a clear difference in error bars. And then you can think of, well, I mean, what happens if I put a model here, how different this is from the expected power spectrum and the expected summary statistics. So this is what we did in the paper, and without entering into much details, the answer is that there is some missing parameter, which is essentially parameterizing the tilt of the linear power spectrum at large scales. So we saw that when varying certain parameters such as omega matter or even NS, we were plotting the resulting power spectrum divided by some fiducial template power spectrum, and what we are seeing is like these changes. So all these are pivoting at some certain scale that we define as K pivot, but essentially what we want to do is to extend our template fit, now being parameterized by 2 extra parameters, in principle M1 and M2, that would capture this change in broadband. So in practice, these two, M1 and M2, are very degenerate, so they cannot be constrained at the same time with data. So what we end up doing is to fix this M2 that in reality can be interpreted as NS according to lambda CDM, and just fit for M1, which in flat lambda CDM models would be essentially omega mater H squared. So if we do this, now we can compare which are like the constraints we infer from this full model, this full direct fits to the power spectrum, or now this called shape fit compression, which would be taking essentially the same compressed variables as before, the two BEO measurements along and across the line of sight, the RSD, and now this extra parameter M that we refer as shape. So now with this complete set of parameters, now we can reparameterize this in terms of lambda CDM variables and compare with this fit. And what we get is that we essentially get the same constraints. So now we can say that when we include this M parameter here, now these two agrees very well, and we have essentially figured out like an optimal compression for this power spectrum into just 4 different parameters per redshift. So we redid the whole BOSS analysis from redshift 0.2 up to redshift 2.2, taking into account LRGs at different redshifts and quasars, and now parameterizing by this M parameter. So we got essentially 4 measurements of these compressed parameters per redshift bin. And after that, these were reinterpreted in terms of lambda CDM parameters with a prior on BBN, because large scale structure does not get any constraint on omega baryon. And with this BBN prior, then we can draw this plot. So you see that how the standard BEO plus RSD analysis was constraining much less information. And just by adding the shape now, we get like very, very good constraints on omega mater and also an improvement on H. So you see here that after doing that, I mean, H we get is still low. It is not surprising because essentially we're still assuming priors on early time physics through this BBM prior. But then the question is how this can help us to determine or infer, say something more about the H0 tension. So this is like a follow-up of this project, the tale of 2 ages, so this talk about, and now all with that I've explained you right now would hopefully make sense. So remember of this plot I just showed you from before. So this is just this paneling here. So this panel shows you how these 2 measurements were improving when you were adding the shape, right? So you can think of how this really works, right? And let's split this plot in more subplots, right? So this is essentially the same. And now we have like several different directions. So for instance, if you think of what this quantity constrains, this is essentially the isotropic BEO. At different redshifts, it has these different degeneration directions, okay? So essentially this is measuring BEO at different times with the BBM prior. So calibrated BEO infers omega mater and H, as I have explained you. Fine. This is essentially this blue line here, what I call calibrated BEO with BBM prior. So the uncalibrated BEO, this is essentially E of Z, so no information on RS, just assuming RS exists and is isotropic. So just taking ratios, we infer E of Z, which in this case is essentially omega mater, no information on H at all. It's at these dash contours here. So now we have the shape. What happens if we put the shape on this alone, just shape? So the shape alone does not constrain anything. And the reason is because the shape essentially is a tilt on the transfer function at large scales. But that tilt is affected essentially by 2 things. It's affected by the amount of matter in the universe, but it's also affected by the amount of baryons due to the baryon suppression. So we need still a BBM prior, in this case, not to calibrate the sound horizon scale, but to calibrate the suppression of baryons at large scales. So with this suppression of baryons at large scales, essentially we can break this degeneracy and infer this line here that is essentially omega mater H squared equal constant. So this has no BEO information on it. And this has no sound horizon information. It is BEO, but without sound horizon. So now we can combine this with this, and we get essentially this red line, which is the shape with uncalibrated BEO, which is a measurement of H, which is independent on sound horizon. And surprisingly, these two measurements agree. They are crossing each other at a certain value. So we can put this into this plot, and now you can think, oh, wait, look, this shape BBN is in the middle and looks like it could be consistent with shoes. Yes, but remember, I mean, if you want this eventually to pick up to higher values of H, you would need essentially low values as well of omega matter. So be careful what you want to happen. So this is essentially the two measurements, the BEO, BBN, and the combined. And you can have a look a bit more closer how this compares to Planck measurements, for instance. And here I'm just showing the full triangle plot. So just let's focus on this. So this is essentially what I was showing you before. And now here, Planck is in this direction. So it's consistent with Planck. Both are consistent with Planck, and both are crossing at the same time. So now if you want to say that you want to modify the early time physics, now you not only have to modify recombination time physics that would change essentially the blue, you also have to modify the physics that they are relevant to the red. And these physics are essentially K equality, or how fast mode 3 enters the horizon when it's expanding. So there is another curiosity, maybe that this is what happens with sigma 8 or the SH tension. So you see here that the standard BEO analysis plus RSD constrains sigma 8 of around 0.8, 85 maybe, fully consistent with Planck. And adding this, well, it helps a bit to like discard some low values of sigma 8, but essentially everything remains inconsistent. So in terms of sigma intention, really, galaxy clustering and Planck do agree quite well. So this is how the picture was before and now with these new early time measurements, but just to reinforce, this does not depend on BEO. So is the first early time measurement that is independent of recombination time physics. So it's like a new proof, like maybe exacerbating these differences. I mean, the error bars are still not super small, it's ±2, but with new DESI data that could reduce up to just more competitive results and maybe just see whether there are some issues. So if this was going to here with slower error bars, it would mean that if you want to invoke some early dark energy to solve the H0 tension, you have to invoke early dark energy to essentially change in the very, very same way, sound horizon scale and K equality scale. If this goes to here, then this is really a smoking gun of that saying that the lambda CDM model does not work well because sound horizon scale measurements and K equality measurements do not agree under lambda CDM. So what will happen, we don't know, data will tell us. But yeah, I think I'm going to be finishing here. So just to summarize, so far, most of the H0 measurements are divided in two camps, essentially early time based, consistent with low value of H0, and late time or direct measurements, which are consistent with high value. So modifications of lambda CDM can happen either at pre-recombination time or post-recombination time. But typically, post-recombination time needs to modify H of Z at low redshift. And these measurements does not have like a lot of freedom due to BEO measurements of H0. So essentially, you have to put the modifications there in the time where you don't have yet BEO measurements. And this is not very easy and not very natural. And on the other hand, we can invoke pre-recombination modifications, essentially early dark energy to modify H0 and therefore sound horizon scale, but then you will need also to change K equality scale. So this new approach, the shape of the power spectrum offers a new probe on H0, sound horizon independent way, and the current precision is ±2, and is currently consistent with both camps. So that's all my talk. Thank you.
Yeah, Hector, we have time for quite a few questions.
Thanks for the interesting talk. It's not clear to me exactly what you call the late time and the early time. For example, this BAO plus BBN does involve both the early and the late time cosmology, right?
Sorry, what's that?
BAO plus BBN constraints on H0. So it will involve both the early time and late time. So like, for example, in the, when you consider like going to the plot for constraining H0, so it seems like it's still, the uncalibrated BO is still more consistent with the late time H0 values.
So uncalibrated BO does not give you any H0 values. It just gives
with the
you
shape.
It just gives you omega matter, and it gives you this band.
Okay, so that it's
Sorry. So yeah, this is BO plus BBN. It gives you this band. It does not assume any early time physics. It's just whatever value of RD is times H0.
Yes, okay. And for the first question, that what do you say for the BAO plus BBN is purely early time cosmology? Like
you essentially need to assume that this formula is true, and
yes,
that you know this E of Z. Sorry, no, not this one. Sorry, this one. You essentially need to assume that you know this with omega baryon.
Yes, so for estimating
you
RS,
can infer this.
And for H0, we will anyway needs the late time.
And then if you get H0, just you get an RD which is consistent with Planck, which is around this, and then H0 has to be 67, 60.
Yes, okay. Thanks.
The shape parameter M that you had to introduce, was that, I missed the point, was that exclusively due to the fact that you were using Eisenstein-Hu parameterization for your power spectrum, or?
No, well, I mean, this is, so you need to essentially smooth the BEO just to isolate the effect of the shape. Essentially, you can smooth the BEO, you can assume Eisenstein hue, or just do a BEO smearing on it. And then the shape of this, or the tilt at large scales of this, is what is sensitive to, essentially what you're measuring is the transfer function. But instead of measuring at CMB times, you measure it at the galaxy. And this transfer function is a complex function, and it essentially depends on the lambda CDM. But in a sort of model agnostic way, I can parameterize it as this sigmoid. And it's quite a good approximation, at least for lambda CDM. And then you can make these connections between these free parameters and the values of your model. This can be omega matter A squared, but then if you allow for curvature, then for neutrinos or an effective would be slightly different.
Second question, you want to comment on these two EFT LSS papers, which also constrained H0?
Right, so they are essentially
with a BBN prior like you did.
Right. So the thing is, with this approach, it's very natural to essentially isolate the different things, right? You have essentially these four parameters, and you can essentially combine. So in their analysis, they have to assume a Boltzmann code, and the Boltzmann code essentially links the baryon prior with the RS. So what they did is essentially to, by hand, put a nuisance parameter in front of RS just to marginalize over time. So essentially, I think it's a very similar approach. It's essentially our sign horizon free. So I would say this is sort of equivalent, but we did that for like all the redshift bins of VBOS. Therefore, we get better constraint, and also we add Lyman alpha BEO, which also helps for the uncalibrated analysis. So that's why the error bars in our case are much tighter.
Okay, just very nice talk. A lot of results need to think through. Can you provide kind of an overview of the other camp, the high H0 camp? Is it really the case that there are multiple independent groups that are coming to comparable results, or is it really being driven by shoes or by one group? Right.
I mean, I'm not really an expert on the high camp. I mean, for instance, this measurement, there was a reanalysis of this by CATS, and that was showing that this is higher. I know that SHUS has been looking for systematics in their data sets quite for long, and they seem to be very confident that there's no systematics that can move this very significantly. Then Holy Cow is essentially quasar, GR, so is the images of quasars at different, you can see how the distortions of the images are affected by GR. I think this can be quite model dependent. And for the rest of them, I mean, I'm not sure, I'm not an expert. They are other ways of calibrating distances based on different things of supernovae, but it looks like they are all pointing towards high values. So how independent they are, I cannot say, because I really know not an expert how, I mean, yeah, it would be good to have blind analysis on these type of things, but I think it's difficult also.
Okay, cool. Colin, and then we should break for tea.
Yeah, hopefully my question is very quick. Can you go to your contour plot where you showed like the red shape plus BBN one, which preferred this, yeah, this one? How does this contour compare to, for instance, the lensing contours, which also lower omega matter, and also maybe F sigma 8, which also, I guess, prefers lower omega matter because F sigma 8 measurements are generally a little bit low?
Yeah, I think they're around here, maybe. Sorry, no, you mean for the sigma 8? So, I think to remember that typically this clustering, at least this blue lies, is consistent with both measurements of S8, right? Yeah, no, I don't have the plot here, so I really cannot show, but I think to remember that, yeah, this is short. I mean, the contours are wide enough that they are, I mean, you also have to remember that, okay, thank you. You also have to remember that depending who you ask, you get different values of sigma 8 when you reanalyze both data.
And looking at this one, so this one's where you've included the F sigma 8, the fourth F sigma 8 parameter.
Yes.
So in what that actually would suggest that to get all four of them to agree and have a high H0, you'd actually have to have a high sigma 8 as well, which is a bit of an issue.
Right. Right. So you have like this seesaw plot. So you cannot move so easily around without messing up with other stuff unless you change lambda CDM model in a specific way that doesn't do that. So as I said, we have a lot of data. It's not that easy just to move around H0 and don't touch anything.
Okay, let's thank all speakers again.